Howdy, this is Jim Rutt, and this is The Jim Rutt Show.
As usual, things we discuss on the show, we will have links to on the episode page at jimruttshow.com. And I know it's annoying to hear me keep having to say this, but getting good reviews is an important part of the podcasting ecosystem. So when you're done listening today, please give us a 5-star review on your podcasting app. And the reason that's so important is that our visibility on the apps is driven substantially by reviews and ratings. And, getting good visibility lets us continue to build our audience, and letting us have a better and bigger audience lets us attract and keep attracting the kind of wonderful guests we've been having on the show. So when you're done today, please give us a 5-star rating. And if you have the time, write us a review. Thanks. Today's guest looks like a really interesting guy. His name's Connor Leahy. He is a machine learning researcher working on advanced general AI technology, things like unsupervised training, reinforced learning, scaling, etc. Some of his greatest interests are in research towards AI alignment and strong AI. Welcome, Connor.
Well, thank you so much for having me.
Yeah, this will be fun. I mean, we got connected on Twitter. Somebody pointed him and said, here's a deep learning absolutist. He thinks deep learning is the answer to everything. And then as we did some back and forth, he goes, well, not quite so much as all that, but I think we'll have an interesting conversation. And as I've dug in, done my preparation for the show, I found all kinds of interesting things that Connor is involved in. And I think I'm just going to jump in because we're a little short on time, unfortunately, and see how far we can get. And if we don't get too far as I'd like to get, we'll have him back for a part 2.
I might just take you up on that.
All right. So first, let's start with one of your projects, which I just found utterly fascinating, EleutherAI. What is it?
So EleutherAI, we describe ourselves nowadays as kind of like a decentralized research collective of just machine learning engineers interested in a certain kind of flavor of ML research, I guess. So scaling large language models, large models in general, and AI alignment and such. So it's like a specific flavor of research. It's, in other words, a glorified chat server. It's a bit more than that at this point. It kind of started as a bit of a joke between me and some friends. We were just hanging out and talking about GPT-3, which is this very large language model built by OpenAI. That was last year. We said, man, it's kind of cool. Wouldn't it be fun to try to build our own? And then a friend of mine was like, this, but unironically, and the rest was history. And so nowadays we're a very active community of really, in my opinion, totally unbiased opinion, really, really great people interested in doing alignment research. We are most well known for our ongoing GPT-Neo project. We are attempting to build and train a full-size GPT-3 type model and release it as open source. But that's not the only thing we're doing. We're also interested in many other kinds of research projects. It's become a really big thing. And yeah, it's just a really great bunch of people.
Yeah, I was particularly into it. We'll get back and talk about alignment because that's obviously a very important topic. But before we do that, why don't we talk about GPT-Neo and GPT-NeoX and why you decided to create them, why this isn't a waste of time since OpenAI has already got GPT-3, etc. I think our audience generally knows what GPT-3 is, but it wouldn't probably hurt to give 20 seconds on what it is.
Sure. So GPT-3 is basically a very, very, very large model, a truly phenomenally large neural network model that is trained on a pretty simple task of just predicting the next token in a text. So it's trained on huge dumps of text from the internet, and it's supposed to predict text given what it's seen so far. So you might give it a sentence like, hello, my name is, and then it might predict the next word might be John or Mary or something, whatever would make sense in context. So this seems like a very simple, basic kind of thing. You can kind of see how this might be a fun little toy or something. But what's very interesting about GPT-3, there's a lot of interesting things about GPT-3 I'm sure we're going to talk about. And basically, it turns out that this just with this simple task, it was capable of learning quite a lot of very useful tasks. In that you can use it for like translation, you could use it to write stories, you can use it to summarize text. There's lots of very interesting things you can do with these kinds of models. OpenAI was the first one to build a model of this kind of size, and they've commercialized it in a private beta form behind an API, which means you can send the model some text, and it will complete that text. It will respond to that text, but you don't have access to the model itself. So I personally think that these models are very, very important. When I saw the paper that came out around GPT-3, my jaw just dropped. I was just like, oh my God, holy shit, this is the future. This is crazy. It's unbelievable, really. And I know there's a lot of skepticism, and it makes sense to be skeptical about big claims and stuff like this. And a lot of this is based on kind of, just hunches, research. A lot of research is about taste. It's about every researcher will disagree on how important something is. But for me, just seeing that just by training this very large model on just a lot of text, it just suddenly was capable of doing very complicated tasks that it was not specifically, engineered to do, seemed very, very important to me. And I think it is, in a sense, I guess what was most shocking to me is just how much, just by making it larger. So previously there was GPT-2, which is basically the same architecture, same kind of training design, very minor differences. They scaled it up 100 times, 100x larger, and it just suddenly its performance just kept improving as a scaling law. I remember you were once part of the Santa Fe Institute. I think they're very fond of scaling laws there as well, power laws.
Absolutely.
And yeah, so what I find most interesting potentially about GPT-3 is this discovery of these scaling laws. Is that as you scale these models larger and their data sets larger, you can see this very smooth kind of increase in performance compared to the amount of extra resources you put into your models. And so I'm very interested in this. I think this is really important, and I have a lot of things I want to research about these kinds of models. I'm just I had many questions with these models, like how hard are these models to build really? Are these laws, do these really hold up? How do these work internally? Is the big question: how do neural networks even work? As far as I consider, no one knows how neural networks work. It's a miracle that they work at all. I find this still utterly perplexing. And so it started as more of a, hey, this would be fun. Hey, let's just goof around. Let's see how far we can get, building this kind of thing. We didn't really expect to get as far as we did, but we found that there was a lot of really interesting engineering challenges. We learned a lot of really valuable information from working with these kind of things hand-on. I guess it all comes down to this belief that I think that these models are the future. Very large, unsupervised, pre-trained models are going to be the future of a lot of technology, especially in the AI field and elsewhere. And I also think there's a lot of risks that come with this. As you've already mentioned, this concept of alignment and security, something I take very, very seriously. I think there's very severe risks that come potentially with these kinds of technologies in the very near-term future. And I want more research to be done about these kinds of models. OpenAI having their model kind of locked behind closed door makes it very difficult for many researchers to be able to actually study how do these things work? How do they learn? What biases do they have? How can they be misused? What kind of internal things are happening with them? My own research, which focused on this kind of security implication, is very much bottlenecked by the fact that a lot of the phenomena I'm interested in kind of studying don't really work with smaller models. They're just too messy. They're not good enough to show the kind of interesting characteristics that I'm interested in studying. So in a sense, it's about unblocking, at least for me personally, it's a lot about unblocking low research academics who can't possibly train a model like this on themselves and allow them to research this really important technology.
So many things to talk about. First, let me hop back up and talk about this issue of scaling laws. You're right, out at the Santa Fe Institute, where I'm still associated, though not nearly as much as I used to be when I actually lived out there. There's this, I think, a list of hundreds now of social science, mostly, but not exclusively, power laws or something. And it turns out you look at them carefully, they're usually not quite power laws. They're sort of maybe power laws in the middle, but they're not at the beginning and the end. Have you found a power law on capability versus model size yet in this class of models?
Yes. So there is a number of papers of this mostly from OpenAI. Maybe all of them are from OpenAI, including scaling laws for neural language models, scaling laws for transfer. There was also scaling laws for, I think, generative modeling. something like this. These are not the exact names. I think Jared Kaplan is on all the papers. At least when I look for these papers, I just go to archive and put in Jared Kaplan and check out all those. And basically what we've seen is that, yes, there seem to be, at least these regimes that we have studied, which is, across, like several magnitudes of orders, like 4 magnitudes of orders or something of different sizes, that there is a very strong connection between model size, the amount of compute you have and the amount of data you have, and the final performance you will get. One of the most interesting things about these studies is that they found that as you have more and more compute that you can put into your model, as your budget for compute increases, it becomes more and more efficient to train larger and larger models. It's actually more efficient to train a really, really huge model a little bit than it is to train a really small model a lot in many cases. There's this interesting thing that as these models get larger, they, in a way, get more sample efficient. They do need more data, but the amount of data they need grows with like a slower power law than the model size that you want to train. So
that's interesting.
Yeah, there's been a lot of really interesting research in this direction.
So briefly, is things like performance on language models, say performance on some task, an exponential on model size or on input? I guess the input databases are the same size. So, what is the other factor when you're, projecting it onto a power law distribution? Is it number of weights in the model, or?
So you can there's laws for all different, given. If you hold one constant, you can vary the others and see what kind of performance you get, kind of. Usually how we think about it is the most useful one that you use in practice is that given you want to use a certain amount of compute, let's say you have 100 GPUs and you want to use them for 2 weeks, that you can then, estimate, okay, I have this and this many petaflops of compute I want to put into this. Then you can check the power laws, like what is the optimum size of my data set? How many samples do I need? And what is the optimum size of model to train for that many steps? Given your number of parameters, you can estimate how much compute, how many flops you're going to need to do one step on one piece of data. So that way you can kind of convert between the different ones and find like the ideal point that will give you the best performance.
Okay, the next one that you mentioned, I'm going to follow up on that too. Very interesting is that the sample size can actually go down as the model goes up. What do we know about the relationship between those two? And maybe actually would help to describe what sample size is and why it's relevant in this case. Sampling rate, I should say.
The best way to understand this, so these are just invented numbers, but basically you can imagine 100 times larger model only needs 10 times as much data to train to completion. So that's kind of what we've seen is that, of course, as the models get larger, you would want more data, but the amount of data you want grows slower given the same amount of compute, given constant amount of compute you're putting into your model, compared to the amount of parameters you put into the model. So as your models get larger and larger, you're dominated more and more by the cost of the size of the model rather than the cost of data. So previously we were in this regime where getting more data was usually the best bang for your buck. That was like the best way to improve your performance of the model. But at least with these scaling models, as we've seen currently, often the best way to improve them is, so this is not, it depends on the quality of your data, whatever, but assume we have like good data and we have the option of either getting more data, like training on more data, or just making the model larger. Currently, it seems to be often the case that we should just train a larger model on the same amount of data.
Interesting. Because I remember for a long time it was thought that the guys with the big data piles would win. But if we're finding there's a big asymptote there, perhaps not, right? And that gets me to my next question. On your site, you talk about something called the pile. What is it, and is it big enough?
So the pile is our curated data set that we created for training GPT-Neo and successors, and we released it open source as a paper. Please cite us. It's basically an 800 gigabyte collection of various data sources. Some of these are sources that have already existed that other people have curated. Some of them are from our own creation, filtering, common crawl data and the like. It's given our current calculations, this amount of text data, which we think is higher quality than, for example, what GPT-3 was trained on, should be enough to train a model up to like 1 to 10 trillion parameters, so that's about like 1 to 2 orders of magnitude larger than our current largest models.
And this is available to anyone who wants to download it. Open source, no gatekeepers, so that's a good thing. And we'll provide a link to it for those of you out there who want to get that. Hey, Carlos Perez, I'm talking to you, man. A friend of mine who's an AI researcher who's a little bit frustrated by the expense, frankly, of dealing with GPT-3, and also has some questions about what goes on behind the curtains. So you have this 825 gigabyte data set. Is it all English, by the way, or is it multiple languages?
We filter for English, so this is intended to be purely English. This was the design decision we made because we were also interested in multilingual data, but it was just so hard, and we didn't have enough native speakers. We wanted to have native speakers to validate the data sets that we're not, just producing garbage, and that was just not possible. We're just a few people doing this in our spare time. We're just hackers in a cave, so we decided to focus on English for the pile, and that's
okay. Cool.
But probably there's going to be some stuff in there that's also not English that went through the filters.
So the next thing is you created your own model that you aimed to replicate the functionality, at least approximately, of GPT-2 and 3. Talk us a little bit about how you thought through that. As I was reading on your site, sounds like you did not choose to exactly replicate how OpenAI did it, but you did a whole bunch of very interesting engineering thinking on perhaps a better, more efficient way to do it. Why don't you take us through some of that thought process? That was really interesting.
Yeah. So, one of the reasons it's different is just kind of the obvious. We don't know all the details of GPT-3. We know most of the details, but for example, the data set was never released. And some of the data set's kind of mysterious. They just have this mysterious books too, and no one knows what that data set is. And OpenAI will not tell us what that data set is. We don't know where it came from or what's in it. We have some suspicions what it might be, but we don't know for sure. So that's one of the reasons we made Pile, because we don't know what the original data set is. There's also some fine details about how the model is trained, what parameters were used, that of course we won't be able to exactly replicate. But also in the time since GPT-3 has come out and we've been doing our own tests with smaller models, one of the great things about scaling laws is that if something works for smaller models, that usually means it also works for large models. That's a big boon. So we've been able to run, a very, very large number of experiments with all kinds of different crazy architectures. And for the most part, the results were always doesn't make a difference or it's worse than the original. The original model is very good. We have found a few things that we are very excited about, including rotational position encodings, which is we wrote a blog post about. Actually kind of a funny story. Apparently, these are already very popular in the Chinese AI sphere, but they hadn't made it to the West yet. And some of our people that we work with who speak Chinese found that on the blog and said, hey, we should translate this and bring it to the Western audience because this is a really, really cool technique. And so the original version of our code called GPT-Neo was built for TPUs. Those are Google's custom homemade ML accelerator chips. We had a very large access to a very large number of these in the beginning, but it turned out that it just wasn't enough for a GPT-3 sized model. There was no way Google's through their TPU Research Cloud program, which anyone can apply to for academic access to TPUs. They very graciously gave us a lot of access to a lot of these to run our experiments. Unfortunately, it was just not enough to train a full size model. So the interesting thing happened last December when a cloud company called CoreWeave approached us, and they basically said, hey, we're interested in having open source, models like these, and we're trying to get into the ML, large scale training space. How about we work together? You test our hardware, and we provide the hardware to train a full size GPT-3 model. Let's do this. And so they've been very great ever since we've been working together with them to build our new code base, GPT-NeoX. There's a bit of a misconception that these refer to different models. That's not 100% correct. It's more like two different code bases. So the original Neo code base was for TPUs, and this new NeoX code base is we've built from scratch. Well, not from scratch. It's actually based on NVIDIA's Megatron code. A lot of transformer puns, obviously, that we've been working on to optimize and scale to train GPT-3 size models on GPU clusters. That was very difficult. Luckily we have some great engineers that have been wrangling terrible NVIDIA and Microsoft research code that in their libraries and full of bugs to get it to work. And right now we're at the point that our code is pretty stable. We're pretty confident that it works as we expect it to. We've trained some smaller models with it, and we're just basically hit by the chip shortage, is that we're just waiting for more GPUs to arrive and be installed.
Interesting. Now, both of these are on TensorFlow on top of it. Is that correct?
No. Neo is the TPUs, though those are based on Mesh TensorFlow, which is like a library on top of TensorFlow. NeoX is based on PyTorch.
Okay. That's interesting. That's a big change. Yeah, I see a lot of people now moving oddly or maybe not oddly, from TensorFlow to PyTorch. Just give me a quick take on compare and contrast TensorFlow and PyTorch, since you've obviously gotten pretty deeply into both.
Use PyTorch if you can.
That's what I keep hearing.
Yeah, TensorFlow just has a lot of difficulties, and it was one of the first things. It was a trailblazer in many ways, but PyTorch is just much easier to use in practice. There's just a lot of very, very nice things. Like the way TensorFlow does it is you have to like define a computation graph, and then that compiles the graph and then runs the graph. So like errors are like really hard to trace back if you can't change the graph once you've loaded it and stuff. But with PyTorch, it's just like running code. Just every time you run a line of code, it just executes on the GPU. And if there's an error, you see the error. If there's like a feedback, if you want to like interrupt the process, you can just interrupt it. So it's just a much more elegant way of dealing with these kind of things. Thing is that you need TensorFlow, or now also JAX, which is like a new thing from Google, to use TPUs. So TPUs require, like PyTorch has TPU support, but it's pretty terrible. So PyTorch is really only good on GPUs.
Well, again, since I got a live person here who's worked with both of them, the compare and contrast between the T chips, the Tensor chips that Google has, and GPUs. I mean, Google actually got access to a little bit of on that experimental program when it first came out, and I flung up some simple stuff and played with the TensorFlow chips. They did seem, I wasn't working them hard enough to see if there was really any functional difference. Since you've worked on a cutting edge performance driven project, what's your take on GPU versus tensor processing chip?
So I would describe TPUs as black magic, like dark magic. You have to sell your soul, your sanity, and in return you gain great power. TPUs are a pain to deal with in many situations. There's like a lot of like weird edge cases. There's a lot of like, there's a lot of finicky things. Like you have to have all your tensors have to have like a constant size. You can't like change the size of things. These are all things you can work around. They're just a real pain. But if you do that, now that we've used both, we must say TPUs do have fantastic performance. They have like these wonderful interconnects. Like I would say the biggest bottleneck for training very, very large models is actually the interconnect speed between chips. Because you have to like split your model between like many chips, and the cables, the connections between them are extremely important. And TPUs really, really have fantastic interconnect. So if you have like a model, like a GPT model or something, and that can scale, and it's very easy to scale from, one TPU to 1,000 TPUs, which is a click of the button. That is very, very nice. And you can get very, very good performance out of them, especially a price per dollar. But in practice, if you want to do anything, if you're not at Google and can't like call up a Google engineer to help you or something, you will be much slower than working with GPUs. GPUs just allow you to try much more complicated or interesting experiments. You can iterate much faster. It's just a very, very pleasant experience. Like nowadays, GPUs are a very mature ecosystem. It's just really easy to work with them. So if you value your sanity, use GPUs. If you have people who are willing to, maybe not give us some of the sanity, TPUs do give you very good performance.
Of course, you have the advantage of having free CPU from CodeWeave. Is that the name of the company?
CoreWeave.
CoreWeave. We'll put a link to them on the site too. Give them a call out. They're giving you all the GPU you can eat. Do you have a sense, if you had to pay for your processing, whether it would be feasible to continue to use GPUs versus TPUs?
Oh God, no. Eleuther has no budget. We function on no budget. We don't raise money, and you don't even accept donations. Like it's like part of our philosophy that we don't accept monetary donations because we don't want weird incentives. We accept only labor and like compute donations, and it's crazy. Eleuther is really a very, very strange scenario in that we have, a bunch of people doing this in their free time with no budget, but we work on a computational budget that, must be millions, equivalent millions at this point.
But you don't know or care. So you really can't say whether if someone were doing this as a commercial project, it would be feasible to do it on GPUs versus TPUs, I guess is my question.
I mean, I mean, doing these kinds of projects is extremely expensive either way. I think, if you're in the order of magnitude that you can afford something, that you're considering affording something like this, it probably doesn't really make a difference. I don't know exactly how much of a difference it would make at this point between TPUs and GPUs. GPT-3 is just so large. You're going to talk about millions no matter what you use.
Of course, there's a difference between millions and tens of millions. Us business guys pay attention to stuff like that, right? A business that might be perfectly feasible if it costs $5 million might not at all be feasible if it costs $50 million, for instance.
That's true. Yes.
Yes. Okay. So the bottom line is you don't know.
Yeah.
So let's get now down to GPT-Neo, which is the only part you have released so far, as I understand it. And according to your site, you have on March 21st, 2021, released a 2.7 billion parameter model trained on your GPT-Neo software. Could you put that in context of GPT-2 and GPT-3? Kind of where does it fall on that continuum?
So the largest GPT-2 model is about 1.5 billion parameters, and ours at 2.7, it's not quite twice as large as large GPT-2 model. The largest GPT-3 model is 175 billion. So as you can see, it's about 100 times more. Not exactly 100 times more, but quite a lot much larger. So it's not the absolute biggest publicly released model, but it's up there. I think there's like one or two models that are publicly released that are larger than ours at the moment. But I have reservations about some of those. I feel like some of those are not particularly good. Maybe I'm biased.
Now, I saw some benchmarking you've done on particular tasks, and it seemed like GPT-Neo could hang in there even with GPT-3 on at least some class of tasks. What have you learned about benchmarking your model versus GPT-3?
So I've learned that benchmarking is really hard. Benchmarking is really quite difficult. And honestly, in my personal opinion, I feel like we, as a field, as a science discipline, haven't yet figured out what the right way to evaluate these models is. Like the difference between on some tasks, the difference between the smallest GPT and the largest GPT is like 4 percentage points or something. But there's a huge difference in subjective performance in using the smallest or the largest model. Like if you use the smallest GPT-3 model, disclaimer, we don't actually know how large the models are with OpenAI side. We've asked them multiple times, but they refuse to tell us what size they actually are. We have some guesses how large they actually are. So actually, we think that the smallest model is probably quite small, and we do think the largest model is probably the full-size model. But it's really hard to tell because OpenAI won't they won't tell us what the actual sizes are. So it's OpenAI has also been kind of stingy about explaining how they did some of their evaluations, so it can be pretty hard to replicate these kind of things. It's evaluations are good, they should be done. It is useful to have these kind of benchmarks, whatever, but I wouldn't read too much into them at the same time. It's more interesting to see a trend, like a power law or whatever, as the models go larger, that all of these tend to increase, rather than focusing, it went up by exactly 0.5%, that means X. Our model also, for example, destroys GPT-3 on certain tasks. Our model was trained on a large amount of academic, mathematical text and code. So our model, annihilates GPT-3 when it comes to math and coding type tasks.
Interesting. Now, when I fooled around with GPT-3 a little bit, as I recall, actually I had somebody else doing it on a Zoom, so I wasn't quite hands-on. Goddamn, OpenAI has not approved multiple requests for me, and I have a really interesting research project. Maybe we can do it on GPT-Neo instead. And we'll talk about that a little bit. But as I recall, how GPT-3 worked was you set up a primer block of text, right? And GPT-3 had a pretty short, small limit on the size of that priming text. And then you put your query in, and then you got your generated output. Is that approximately correct on how these models work?
Well, actually, what you describe as like context and prime are actually the same thing. So you can imagine these models have like a window they can see, which is 2048 tokens. A token is not quite a word, not quite a single character, something in between, and it can see inside of this window. So you can fill up as much of the window as you want with your prompt, and then you can have it complete as much as fits into that window, basically.
I gotcha. Okay, so that's actually so you say add the same 2048 limit.
Yep.
Because that struck me that was a big bottleneck, and if you could make that limit, for instance, 1,000,000, it could be much more interesting.
So the problem is that the training cost of training a transformer is quadratic in the size of its window.
Ah, okay. So that's a very key engineering decision.
Yeah, exactly. It's the 2048, in my opinion, is actually already pretty good. Like you could do a lot of very good things with that size. It's also a problem of training data. There's very little training data that's 1,000,000 tokens long, other than maybe books. And you can do a lot with these smaller token windows if you're clever about it. Like the way I think about it, like us humans, we also only have short-term memory, which is 7 plus minus 2 objects or whatever. Which like I can't remember a 20-step derivation in my short-term memory. It feels like we're due for some kind of scientific breakthrough that's going to make these models use long-term memory in some kind of way, some kind of like scratchpad or some kind of memory tokens or something. Not currently, but I expect something like that to emerge in the near future, because that quadratic bottleneck is a pretty big problem when you get to these large sizes.
Interesting. So let's now move to, and this may be a little tricky, but I think you're up to it. Give the audience an example of something you might do with one of these trained models using these this size 2048 tokens. So what would be your prompt and what might be your output? What's an application?
Here's a great example. A good friend of mine is working on a video game using GPT-3. Codename Electric Sheep is the name. And the idea is that it's a dream simulator. So you lay down in bed and you enter a word of like what you want to dream about. You could say, I want to dream about a beautiful forest. I want to dream about a cyberpunk dystopia. I want to dream about whatever you want to dream about. And then what he does is that he then queries a GPT model with like prompts to generate NPC speech and like world description. So like one of the things he does is that he would, for example, say, I don't know if this is the exact prompt he would use, but like just to give you a feeling for it, it might be like you might prompt the model with, wow, I really sure do like topic, and then the AI might continue that by giving you a whole explanation of why he likes it or what it thinks about it or whatever. You can so this is something I haven't yet had the time to really talk about. But the most fascinating thing of using GPT-3 yourself is that it is really a very different experience in my opinion, from using other like AI systems or other like computer systems. And that very often you can just ask it to do things, and very often, not always, but like very often, it will work. So, for example, it used to be that with like GPT-2. To generate, one of the tasks we needed for the video game was to generate names for the NPCs. So with GPT-2, you had to like try all these like complicated prompts where it's like, you gave it like a bunch of example names in like a list format, and you like hoped it would like, continue the list format, but that didn't always work or whatever. But now you can literally write, this is a video game about dreaming. In this dream, it's about X. Here are the following characters, : and it will just pretty reliably just output like a list of pretty relevant character names that you could just parse right out of there.
That is pretty amazing. And as you discussed earlier, GP2 and GP3 architecturally are quite similar. And it's just the difference of a much bigger data set, or not a bigger data set, but a bigger model with many more parameters. So essentially more richness of whatever the hell it is that goes on in the interface between language and cognition is a better statistical representation in the GPT-3 model than in GPT-2. Is that approximately correct?
Yeah, exactly. It's so like this is probably the person who connected to you that said I was a maximalist. He's probably talking about my some of my thoughts about and some of the things I've said in the past about GPT-3 and such. So I think people very much underestimate how powerful GPT-3 is and how different GPT-3 is to other technologies. I really think this is a incredibly important discovery, like just scientific discovery, that this is possible, that you could just scale these things up and they just gain all of these weirdly human characteristics. Like here's one of my favorite examples. Two friends of mine wrote a paper where they tested. So in the original GPT-3 paper, there was a translation task where they're translating like English into French. And the way they tested this is with a prompt that was like English, English sentence, French, and then the model would fill in a French sentence. My friends found that they could get statistically significantly better performance, like several percentage points, like not an insignificant amount, by instead making a prompt like the following sentence is translated by the masterful French translator as, and then that. But putting in the masterful is really important. If you don't do that, the performance degrades. Telling the model, very often with GPT-3, if you just tell the model, you are a super intelligent, very helpful model that wants to help humans, makes it like nicer and like give you more useful answers. And my explanation for that is that if you think about the task the model was trained on, it wasn't necessarily trained on being correct or giving the correct answer. It was trained to basically emulate the median internet user, or to predict, or to role play, to LARP as whatever is given the text. So if you tell it, please role play as something super intelligent, in a way, it will then try to simulate something more intelligent than the median internet user. And I find this absolutely fascinating.
That is really interesting. It actually fits in well with my proposed research project, which I'm going to run by you to see what you think. What I proposed to OpenAI was, my home field in science is evolutionary computation. And you've pointed out that these changes in the prompts, even subtle and non-obvious ones, make quite a difference in the output. And so what I proposed was using a kind of simplified form of genetic algorithm to explore prompt space, and then use mechanical Turk as a validator on the output. And like an example like you gave, any of these examples, fairly simple ones, and then just basically iterate between GPT-3 and mechanical Turk, and use GAs to select the genes, essentially being the prompt, and seeing if that converges to better results. Does that make sense to you?
It does. It does make sense to me. There's actually a lot of research. I actually work at something kind of similar to that for my own projects. So there's interesting. One of the things, again, I want direct access to a GPT model is because, like, what you describe is like a zeroth order optimization method. Evolution is kind of like there's like zeroth orders. You don't have any gradients.
Yeah. The weakest but most general of all methods, right?
Exactly. Like, you could do a lot with evolution that you can't really do with gradient-based methods. But of course, it's also much harder to optimize. So there's been a lot of very interesting work in like the last just few months on like continuous prompt programming. So where you don't give it words. So like the way GPT-3 works is you have these tokens, and each token is then put into an embedding space. So it's like transformed into like a vector, and this vector, which kind of like encodes what that token means, is then the input to the actual model. And what they found is that you can kind of, if you have a task, you can backprop through the model to like find like token embeddings that are in between words. They're not real words. They're like just like these abstract concepts of like, something, and you can use those to get the model to like significantly perform better on different tasks. There's something called like prefix tuning and such. I could leave you some papers if you're interested in this.
That'd be very interesting.
Yeah, so if you have access to the model and the task you want it to perform good on, you can use first order optimization, so you can backprop through the model to get these like continuous representations that can give you really good performance. I personally also work I'm very interested in using like reinforcement learning and stuff like this to learn human preferences. So something I'm interested in is training. So this is based on work done. Last author was Paul Cristiano at OpenAI, where basically he trained a model on human exam. So humans labeled summaries of text. So there was like a text, it was summarized, and humans labeled whether the summaries were like good or bad. He trained a model to predict whether humans would like or dislike a certain summarization, and then he used that model as a reward signal for a reinforcement learning algorithm to fine-tune a GPT-2 model to produce better summarizations. And the final model actually outperformed the human benchmark.
Wow. That's really interesting, because my interest has always been in search techniques that allow the power of the back end to be searched at some high level, at a high order, whether it's GAs or GPs or other funky kinds, particle swarm optimizations or other forms of algorithmic search in a space like this. And I think this is very interesting that people are starting to do this, because it seemed obvious to me that it's the kind of thing that ought to have been done, but none of the early papers were doing this at all.
Yeah, absolutely. That's what I mean when I say I think we haven't even scratched the surface of what these models are capable of, or like what the correct way to prompt or control these models really is. I think we're in a very, very much in the early stages of understanding how to use and harness what these models have actually learned.
And then, as I understand it, this first order optimization you talked about, where you use actually the abstract token space rather than words, is something one could not do on GPT-3. They don't give you any access to it, but one could do it on GPT-Neo.
Exactly.
So there's a sales pitch for GPT-Neo, that if you want to work in abstract tokens rather than actually words, then you'll need actual access to the model. Which actually, I'm going to go on a little rant here. This isn't the first time I've run into this. Goddamn OpenAI, right? When they first started out, it was all going to be open source. Give it to the world. Gift economy. Various billionaires staked this damn thing, and it was going to be given to everybody. Well, guess what? They very quickly turned tail on that one and have God knows what kind of bizarro deal with Microsoft. And what's up with all that? Do you have an opinion on what's going on at OpenAI and why they have defected against the world on their original commitment to be all open source?
Oh boy, do I have opinions.
Yeah, let her fly. You're on the Jim Rutt Show. You can say whatever the fuck you want, right?
I appreciate it. But honestly, as much as I have opinions, in a way, they might not be as inflammatory as you might hope them to be.
Oh, shit.
I have a lot of friends at OpenAI. Like, I think a lot of the people at OpenAI, like, I was very, if you know some of my history and stuff, like, I've had my disagreements with them. I've had, like, very severe disagreements with some of these people and, like, how their policies are and whatever. But I must say that once these people actually give me the time to talk to them, and I've, like, heard their arguments for what they're doing and why they're doing it, I've been surprised by how often I was like, okay, I actually kind of see where you're coming from here. So it's also worth, so basically here's been my timeline of how I feel about OpenAI. So when OpenAI first did the GPT-2 thing, I was like, this is incredibly silly. I think this is stupid. This is when I was like micro infamous for like 2 weeks for creating a version of a GPT-2 and threatening to release it. And I read like a terribly long, cringy manifesto about why I think this is a good idea. I decided not to, because I actually heard some of their arguments. And basically, I think for they had a very good argument. The argument was basically just, yeah, GPT-2 is probably not dangerous, but someday some model will be dangerous. And it's a good idea to have these discussions now and like think about how should we think about responsible disclosure, how should we think about deployment and such. So in a way, I felt like an asshole, because I was like shaming these people who had reasonable security concerns. I think they were wrong. Like, I had objective disagreements with them, but it was a reasonable thing to be concerned. So in that case, I would have called myself, I think I was being the dick in that situation. Things have changed slightly, in my opinion, since then. So I think that was nowadays. So like, I've talked to OpenAI people who've also said like, yeah, we hate the name. Like, we should have never used this name because I think it was never the intention for it to be purely open source. If I understand this correctly, that was never actually the goal. The goal was always is like, I don't know if you've read the OpenAI charter and like whether or not it's crazy or cringy, to each their own, but they take the things they say, at least like the people I have talked to, take it very seriously, that AGI will come, it will change everything. This is going to be bigger than the Industrial Revolution. And they do, and as much as I want to rag on OpenAI, they do have the charter, they do have this like weird corporate like windfall clause. A lot of people say the windfall clause is kind of silly. So for those who don't know, the windfall clause says that after OpenAI has paid, I think 100x returns to their shareholders, the rest goes to nonprofit. So it's kind of like a capped return. Of course, the cap is ludicrously high. It's like 100x or something. But if you take the argument seriously that this could be a bigger than Industrial Revolution, which, you may or may not take that seriously, then it is at least a sign of good faith in a way for them to have such a thing like this. I must say, though, that in like the last year, like ever since the GPT-3 thing, I've had much more severe concerns about OpenAI's direction. So I don't know if you've heard also recently there was an exodus where like a lot of top people left OpenAI. A lot of them I knew. Basically, all the people I really liked left. Not all of them, but most of the people I really looked up to kind of left. Especially like a lot of the safety team and such, which is like not happy about that. I've also just had some interactions with people like Sam Altman that I found that they have opinions that I don't really agree with, or I find are a bit worrying in that regard. So overall, currently I'm at the point of like, I basically don't trust OpenAI anymore. I think they've gone way too hard commercial with this GPT-3 thing. And even if you disregard the commercial thing, if you take these safety things seriously, so let's assume I believe everything OpenAI says, that, AGI is coming, we're going to build it, it's going to change the entire world and make $1 quadrillion or whatever. Let's just assume these things are true. If they take these things seriously and they take these like arguments about safety seriously, in my personal opinion, the most dangerous thing that they did is just to tell the world that scaling was possible. Because before that, scaling was widely considered to be a joke. Everyone's, it was like, this is a dead end. Don't do this. Like, whatever. We need to more smart architectures, not bigger models or whatever. But now that OpenAI has shown with GPT-3 that scaling is at least one of the paths forward, and it's like an easy path. You just need more GPUs. Just buy more GPUs. Anyone can do that. In many ways, they've accelerated a race towards more powerful AI technology with out of control, lack of safety concern, research. So I find there's a lot of contradictions in the communications from OpenAI. A lot of my favorite people left. I think, I'm very not happy with the current state of what they've been doing, and I do fear, what they might be doing in the future.
Yeah, rant off more or less. So I've always wondered if the GP3 is in the head fake to get people going down a different road from the real answer. Well, maybe we'll talk about that in our next episode. So that's a perfect place to pivot, and this will be sort of our last topic. And I would like to get you back to talk about all the other things on my topic list here. So I will ask my guy George to hook us up sometime in June to continue this conversation. But let's now pivot to the idea of alignment and AI safety.
Yeah. So alignment or AI alignment kind of describes like a certain niche within the wider world of like AI safety and AI ethics. So it's like I would describe it as like a certain flavor. It's like, it's like a certain type of person involved with it, certain, founder effects. And, it goes back to people like Nick Bostrom, Eliezer Yudkowsky, and stuff like that, kind of like the founders of these ideas. And basically, the way I would like to explain it is just, I would like to ask like all people working on AI, what happens if you succeed? What happens if we succeed? If it just works? We have superhuman intelligence. It's 1 billion times smarter than a human. It can solve any problem. What then? How can we control such a thing? If it's smarter than us, obviously it can trick us into doing whatever we want. We already can't control, our governments, our economic systems, our computer programs. Just think about computer safety. We have bugs and, software flaws everywhere. Now if you have a bug in your software, okay, maybe your browser crashes or something. But what if it controls the entire economic system of the planet, or it's curing cancer or whatever? So basically alignment is this question of like looking just a little bit into the future, into like these really powerful AI systems, that are as smarter than humans. And just this question of how would you even, get them to do good things and not bad things? What does it even mean? Like, how would you formalize this idea? How would you stop them from doing something very dangerous, potentially? If they're very powerful, they might well be able to doing very, very dangerous things.
Interesting. Yeah. And so then how does that relate to GPT-3, which at one level, it's very impressive, but it doesn't look like they're going to turn the universe into paper clips anytime soon.
You bring up the paperclip maximizer, a classic, of course.
And we know it's misleading, but nonetheless, the class of data, there's different kinds of risks, and GPT-3 is nowhere close to an obvious existential risk like the theoretical paperclip maximizer that Eliezer and others love to talk about. I've had some interesting conversations with Eliezer back in the old days, before they became Miri, and he's definitely an interesting dude. But anyway, that'd be another conversation for another day. So where are the risks around things like GPT-3 or the misalignments with the good of humanity?
So there is like two prongs to this thing. There is the concrete things that, GPT-2, 3 could do, stuff like misinformation, biased language, like, used for like troll farms or whatever. Personally, I think you've seen my extremely long Medium posts about this kind of stuff. I think these are real concerns. These are real, but they're not existential. Like, I don't think, we're going to paperclip ourselves by having mean Twitter bots. Like, I don't think it's good that these things happen. And I think, we should figure out ways to address these problems, but they're not what I personally work on. So I'm more concerned about an essential risk. So the reason I'm interested in GPT-3 and these types of models from an LLM perspective is that I think there really genuinely is a appreciable probability. Like, I personally put like 10 to 30% chance that the first transformative AI, so like real, paperclip level threat, will just be a very, very large, trained on GPUs, made with PyTorch, pre-trained on internet data system of this kind. So there's a lot of reasons why I think this might be the case. Again, like 10 to 30%. Like, of course, who knows unknowns? Who knows what's coming down the line? But for the first time in my life, I look at these like transformer-based models, these like large scaling models, and I see, as far as I'm concerned, a direct path to AGI. If these scaling laws hold, and if they work for different modalities, whether or not text is enough for AGI is kind of controversial, but we've already seen that these scaling laws also work for images. They work for math. They work for sound, video. They work for all of these different modalities. You can use the same architecture to combine all of these different all these different things, and it seems to me that I also have like some like hunches about like how this relates to like, it also seems like the brain also does like some kind of like unsupervised learning-ish thing in the neocortex that seems to be really important. Like, in a way, a human brain is just a scaled up chimp brain. Like, it's all the same parts, it's just 3 times as large. So whether or not that's true, it's not super central to the argument, but I have a pretty strong hunch that there is a connection there. And it seems to me that seeing how between GPT-2 and GPT-3, how we have like these really interesting, like seemingly intelligent things emerge. Like of course, people would never say, oh, GPT-3 is like, sentient or something. Of course not. But then again, you can talk to it. Like, you can talk to it like a person, and it works pretty well. It is kind of weird. Like, if someone from the future came to you and gave you a black box, and the black box just talked to you like a person, you would also have like some like, this seems concerning. This seems like something we might want to research more carefully. And as we've seen that, the difference between GPT-2 and GPT-3 is like really hard to quantify. We've talked about this with like evaluations. It's really hard to like give like I can't predict. I couldn't predict ahead of time what GPT-3 might be capable of. In the same way, if someone trains a trillion parameter, 10 trillion, quadrillion parameter model, I don't know what it might be capable of. I think there's like truly a non-zero probability chance that you train like a quadrillion parameter model or something, and it has like some so good simulator that if you tell it you are a paperclip maximizer, your actions are : that it might very well just do that. If you then hooked it up to some kind of actuators. Of course, no one would actually do that, but I feel like this is an interesting test bed to start to research like these generalized, like models of like complex data and how we might be able to align them, because they're also not yet dangerous. Like, I don't think GPT-3 is going to paperclip the universe. I think that's good, because I think that means we can do like kind of stupid experiments with it that we might not want to do with an actual AGI.
Interesting. Well, I think we're going to wrap it up there, because this is a natural branch to episode 2, where I'm going to come back and say, here are several reasons why I don't think GPT-X is actually AGI. And that was the original reason I think we were connected. I'm really looking forward to this, the next conversation. And I also want to dig into and get your updated versions on your counting consciousness articles, which I found I was holy shit when I was reading those things this morning. Actually, I'd love to talk about those, and they were written a while ago. I mean, was it 2 years ago? That's ancient history today. I'd love to get your perspective on those things as well. So, Connor Leahy, I want to thank you for an excellent episode of the Jim Rutt Show. I look forward to having you back.
Well, thank you so much. It was great.
Indeed, I really did enjoy it.
Production services and audio editing by Jared Janes Consulting. Music by Tom Muller at modernspacemusic.com.